Swayam Prabha. Digital India. Educated India.
Hello all, welcome to Astrochemistry. This is lecture number 79. So in the previous lecture, we were discussing about the chemistry of comets, and I just introduced this phrase called as steady state approximation. I told you that this is particularly valid and invaluable in chemistry of comets, which is quite analogous to interstellar reactions. So this idea of steady state approximation is quite useful for interstellar reactions also. Why is it? Well, the commonality being the series of reaction networks. We have a lot of reactions as part of a reaction network in both interstellar reactions when we consider molecular evolution in the dense molecular cloud, as well as the photochemistry that is happening in comets. Okay, so I just gave one mathematical expression called as d of I by dt is equal to 0, where I is some intermediate. Now let us look at some more aspects of the steady state approximation in this lecture and why it is important. Okay, so I just retained the content from the last lecture here so that it will be useful for the purpose of continuity. I shall continue here. Okay, so I won't start with page 1. I'll just go to page 2 here. Okay, please note this. Or you know what? I'll just modify it. I'll call this page 1. And this shall indeed be 2. And this will be page 3. So now I'll just continue right here. Okay, now I'll tell more about this the specific equation right here, right now. So, see, take a reaction of the form A giving B giving C. This can be part of a reaction network. This is just one, or a simple two-step reaction. Okay, the rate coefficient. We call that in, I think, lecture 72. I introduced the notation rate coefficient. You may go back and look at it. And for this step is K1, and this is K2. Now, if you consider this as the well-established mechanism, in other words, this is the way we know that. When I say we know, right, I mean we strongly have evidences. We have enough strong evidences to believe that this is the mechanism via which A is getting converted to C. A and C are generic species. Okay, so we know that, this is the mechanism for the formation of C, and B here, right, is some intermediate. So it's an intermediate which is referred by I. So by I here, I'm talking about an intermediate. Okay, so I is just some intermediate. So now your rate of formation of C. So your C is coming from B, which is an intermediate. It is not the starting point. Okay, so B itself is coming from A. All right. So your rate of formation of C, okay, right, is given by, because it's an elementary step, I can write it as a linear function. That's why I told you that the mechanism is known for this reaction. This is coming from the fundamentals of chemical kinetics. Okay, so dC by dt, well, the square brackets refer to the concentration. I think we discussed this in lecture 72 also. Okay, is given by K2 times B. Now, I'm not saying any general function. It is particularly a linear function because it's because we know the mechanism. All right. So this is what it is given by. But noting that your B itself, right? It is formed from A. In other words, this is its formation rate, but it is also getting destroyed. So this is its destruction rate. So noticing that your B cannot be used as such. The formation of the overall rate of change of B itself has two expressions. All right. So now if you were to, like incorporate all these aspects and do the integration subsequently, you will get from here, okay, overall, right? I mean, after integration also, after doing all the math, I'll leave it to you as a homework. See, we can do it, but it will be time consuming, and I have to teach so many more cooler aspects of astrochemistry. Okay, so I'll just not do the math here. So using this idea in this expression, right? Integrating also, I'll give it to you as a homework. Derive it. You can easily see that your concentration of C is going to be given by this expression, your A naught, which is the initial concentration of A, whatever you take with, times 1 over K1 minus K2, 1 plus, this one is outside this term, okay, please note it. So this is going to be given by 1 plus K2 e to the power minus K1t minus, I think I'll just confirm the sign also, yeah, minus K1 e to the power minus K2t. So what I've written here is, this is K2 times e to the power minus K1t minus K1 times e to the power minus K2t. Now I did not derive it, but you can derive it. But the point I'm trying to make is, even for a simple two-step reaction, right? Even for a very simple two-step reaction, the overall expression for finding the final concentration is beginning to be complicated. It is not complicated as such, but it is beginning to be complicated. All right. So note this point. So this is somewhat beginning to get complicated. Now, what do I mean by complicated? Well, it just has a lot of terms, and you need to determine a lot more rate constants, right? And to do the computation is slightly harder. So this is the case for even a two-step reaction. But if you actually, talk about a more complicated network, be it as part of cometary chemistry or interstellar chemistry, the expression easily will grow much more complicated that sometimes it would be very difficult to solve. That is why the steady state approximation is introduced. What the steady state approximation does is, so this is here, it's somewhat beginning to get complicated, which implies for networks containing more reaction steps. What network I'm talking about? I'm talking about a network of chemical reactions. Okay, so for networks containing more steps, see, by steps I'm just talking about the individual reactions. It's a colloquial usage. Okay, so for network containing more steps, the rate expression, so I'm just continuing from here. Okay, so for networks containing more steps, the rate expression will be much more complicated. And to avoid it is why you use the steady state approximation. Let us, for example, consider the same reaction, okay, to illustrate how we know this complication is overcome, to see how steady state approximation eases our job. Consider the same reaction, A giving B giving C, and let the rate coefficients be K1 and K2. Now, this is the intermediate. We saw that your the rate of change of the concentration of B is given by its formation rate minus its rate of reaction. The minus sign comes because it is getting low, its concentration is decreasing, minus K2B. So now we have this expression right here. Okay, now, but according to the steady state approximation, this becomes 0, right? But what is the validity of this approximation? I mean, just because something is complicated, we can always make approximations but it should also be valid, right? The validity of the approximation, especially in the context of both cometary chemistry as well as interstellar chemistry, is that intermediates are short-lived, right? That's why it's an intermediate. It is not the final product itself formed. So therefore, the validity of the steady state approximation is that, so this is 0 by your steady state approximation, which we call as SSA, and it is valid because of the idea that intermediates are highly reactive and short-lived. Okay, that's why it's valid. So it's not just an approximation used to ease the complication, but also it is physically sound and sensible. Okay. Now, for example, if you have an intermediate which itself is stable, in those cases, this approximation is a bad approximation. But hey, by and large, when we talk about the chemistry of molecules in the dense molecular clouds in the ISM, as well as the chemistry of comets, the intermediates are going to be highly unstable. So therefore, this is a wonderful approximation which not just eases our computation, but is also based on sound physical logic. Okay, that's it. So the validity of the approximation is that the intermediate B is highly unstable and reactive. So at any point, you don't see any sufficient accumulation or buildup of the intermediate itself. And that is why its concentration could be set to 0. And after setting it to 0, you get that your is nothing but, I'll leave it to you as a homework, as to how you do the math and put it together. Homework. Do you have this? Why am I giving it as homework? Because I don't want to, waste time in the lecture itself. Okay, I want to carry on with some more concepts. Okay, that's right. So this is it. And having seen this, right, once you integrate it overall, containing K1 and K2 and all those, your concentration of C is going to be given by, I've written it down here, the concentration of A at 0 time times 1 minus e to the power minus K1T. So look at how, look at this expression over here, right? It contains so many more terms, and how easily it got approximated to this one. This is much easier to solve. Okay, so this is the validity of the steady state approximation. Now, in fact, this is used routinely in a lot of chemical networks, right, that are part of the interstellar chemical reactions as well as cometary chemistry. So please note this point, that steady state approximation is a wonderful tool that helps simplify the mathematics, the complication with the arithmetic, right, when it comes to finding the rates of astrochemical reactions. Okay, that's it. One important point, it is that, see, the steady state, right, need not be always applicable only to chemical reactions. Okay, even for physical processes. Okay, even for physical processes, such as, for example, you consider the formation of a planet, right? Even then, let's say, as we discussed, during perhaps in the previous lecture and the one before it, how Earth was formed from a bunch of meteorites, either via cold accretion or hot accretion. In any case, mass is getting accrued together, right? So there may have always been some intermediate stages. Okay, so this concept of steady state approximation is not just valid for chemical processes. The steady state approximation is not just valid in the context of chemical reactions, but is generically applicable to many physical processes. such as, for example, formation of a planet. So whenever you assume LTE, right, that is local thermal equilibrium, you know that there's going to be some intermediate form. See, how is a planet formed? The rocky masses coming together and passing through various intermediate stages. You have the final stage where sufficient mass is generated, right? So for all those intermediates also, you can use the steady state approximation. That is the rate of formation of the intermediate. The rate of accumulation of the intermediate is negligible. Okay, that's it. So please note this point. So having said this point, right, we shall now actually, move from cometary chemistry and study the chemistry of planets. All right, that's what we're going to do next. Oh, and by the way, before we actually study the chemistry of planets, note a small detour, okay? A small but important detour and clarification. See, we are on the subject of intermediates, right? So while talking about intermediates, I want you to go back to lecture 71. Go to lecture 71 and lecture 72. You may refer to your notes from this, or you may also go look at the videos themselves. I want to correct a mistake I made. Okay, want to correct a logical mistake. Now in 72, I'm just talking about the first 5 minutes. In lecture 71, somewhere near the middle and the end part of it, and lecture 72, the initial part. I'll also write it down. Lecture 71, the mid portion somewhere, middle and end portion. And in lecture 72, I think the first 5 minutes, 5-ish minutes, because we are on the topic of intermediates, right? I thought I should. This is an opportune moment to talk about that. I had given you an example of some arbitrary reaction of the form A plus B giving I1, which is giving I2, which is giving the final product. Now, I told you that here in this sequence, if we took I1, which is the intermediate. This I is me, okay, right? Yeah, the lecturer, okay, right? So I told you that we took I1 to be most stable. That is having the maximum value of magnitude of delta G, okay? So let's say, that this is delta G1, delta G2, and this is delta G3, okay? I also told all delta G's, all individual delta G's, that is delta G1, delta G2 and delta G3 are negative, okay? Now that is the wrong statement. So this is the wrong statement. I want to correct it right here. Okay, please note that this was a wrong statement I made and I want to correct it. It is, I'll write it here. Why is it wrong? Well, because if I1 is the most stable one, then the math doesn't hold up. Okay, delta G1, delta G2, delta G3, they cannot be following this order. Okay, I'll explain just a bit further now. It is that let's say that this is delta G1. Okay, now A plus B giving I1, delta G1. Let's say that including sign also, this is going to be something like minus K. Okay, now for the next step, I1 giving I2, your delta G2 has to be some positive number, because I1 is the most stable one. right? I1 is the most stable, so therefore your delta G has to be positive for this step. Okay, please note this point. Likewise, but notice that your magnitude of K is greater than the magnitude of L. That is the beauty. Okay, right? So then let's say for I2 giving final product, your delta G3, the order I think that we took was I1 is the most stable, and in terms of stability order, I1 is more stable than I2 than the final product, right? Order of stability. So what I've written is order of stability. I1 in the final product. Okay. So therefore, this is also, let's say this is M, right? Now this is also positive. This is including the signs. Okay. So including, and because my final product is less stable than I2 also, so therefore this is also positive. Are we clear? In other words, the reaction profile is going to be looking something like your delta G. Okay, let's say this is your initial reactants and products, A plus B, and let's say this is I1. This is stable. Okay, so this magnitude is going to be your negative K, and this is some reaction coordinate. Go back to lecture 7 or 8 to understand what reaction coordinate is. And from I1 to go to I2 is positive. Okay, and from I2 to your final product is also positive, right? But the overall reaction is still the overall delta G, your delta G net is equal to minus K plus L plus M. Let's call that, something like N. Okay, right? This, including the sign, it's going to be minus N. So the net reaction, right? The net delta G is still negative, but the individual steps need not be negative. And this is what is referred to as the condition that absolute thermodynamic control is not that relevant to the interstellar medium. Okay, so even though your net delta G is negative N, okay, the individual steps need not all be negative. Please note this point. Okay, so the mistake I made was I told you an illogical statement that the individual delta G's also have to be negative. That is incompatible with the previous statement. All right, so please make this correction in the middle and towards the end part of lecture 71, and also the first 5 minutes of lecture 72. Please be clear about this. And along with this, this clearly tells you that how we know the concept of thermodynamic control. Go back to lecture 71, okay, right? Pans out in the interstellar medium. Okay, how the idea of thermodynamic control pans out in the interstellar medium, wherein even though some individual steps can actually be having like positive free energies for the reaction. Okay, the positive free energy change, the reaction will still proceed, right? Whereas on Earth, it is I1 that will be formed because that is the most stable species if you give enough time. But in the interstellar medium, well, because of the sparsity of the interstellar medium, your final product, even if it's above some intermediates, they could be formed. Okay, so please make this correction. What prompted me to tell this correction now? Well, we were discussing about intermediates, steady state approximation and intermediates, and thanks to this error being spotted, I could now clarify it. Please note this. Okay, so this was the error clarification while we're discussing about intermediates. Now let us go back to the study of planetary chemistry and continue with the rest of this lecture. Okay, we now have an estimate of the age of the solar system, which is approximately 4.5 billion years. Okay, now it is postulated. Okay, it is postulated based on various experimental evidences about which I'm not going to talk about in this class right here. Okay, it is postulated that almost, all of the planets, right? Almost all of the planets in the solar system got formed roughly, okay, not in the present form, but the structure of the solar system, that is having, the 8 planets and 1 dwarf planet, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto. Okay, they all formed roughly around the same time. Okay, that almost the solar system got formed roughly around the same time. Note, not in their present structure, not with their present structure. Okay, we're talking about a primordial form, not in their present form. So what I've written here is not in their present form. You get this point, right? So as soon as the solar system was born, okay, I use the phrase born again colloquially, all of these planets also got formed right up front, but there may definitely be some structural changes from the current era. Okay, please note this, current epoch, if I can use the word. Okay, what experimental evidence are we talking about? Various notions such as getting samples from these planets, okay, these various planets and the satellites surrounding them, and by comparing it with the composition of the solar nebula. This is the experiment. I won't go into more details right now. Okay, so this is the indirect evidence for this statement that I've written here. Okay, so the planetary structure, was almost formed immediately, and very interestingly, the rocky planets. Okay, now what are the rocky planets? I'm talking about Mercury, Venus, Earth, Mars. So they stay closer to the sun. Whereas the gassy planets, in fact, some of them are called gas giants. The gassy planets, we are talking about Jupiter, Saturn, Uranus, Neptune, and Pluto. Pluto with a star. I'll come back to the star. Why? Because Pluto is strictly not a planet. It's what is called as a dwarf planet. They stay, significantly away from the sun. All right. There's actually a reason for it. So how do I know that these are rocky and these are gassy? It can also be, estimated from the mean density of these planets. I'll come back to that. Okay. But, I'll just end this lecture by telling you the reason for this statement here. It is that, see, and predominantly, when I talk about gases, most of the gases are going to be hydrogen, helium, and some of these lighter elements. Okay. Now, further away from the sun, the temperature is lower. Okay. So the reason is that further away from the sun, the temperature is lower. This is a general knowledge statement, right? Yeah. So as the temperature is lower, the gas particles can therefore escape easier. Escape easily and accrue to form giant gas balls. And especially, the condensation temperature for these gases is not sufficient, is not reached. And that is why they stay very far away. Okay. Whereas the rocky planets, they contain solid structures. But the rocky planets with containing a significant solid state structure, right? The temperature is like sufficiently high for condensation form the solids. So that implies why they are closer to the sun. Okay, so basically there are two types of planets, the rocky ones and the gassy ones. The gases just escape away. So they escape and then they keep accruing masses as more and more build up. And so therefore they continue to stay away. Whereas the rocky planets, enough temperature was reached for the formation of solids, and hence they are much closer to the sun. All right. So on that note, I end this lecture by telling you that in this lecture, summarizing this lecture, we discussed about the steady state approximation and its applicability to cometary and interstellar chemistry. I also told you that the steady state approximation is not just limited to chemical processes, and this was followed by me correcting a mistake I made in lecture 71 in the context of intermediates, and I basically introduced you to planetary chemistry, informing you that the rocky planets are closer to the sun due to the temperature being high enough for condensation, whereas the gassy planets, where the gas molecules could fly away much easier, once they form, they happily start accruing more and more, and so they stay further away with the temperature being low. All right, so that is the crux of today's lecture, and I shall meet you in the next lecture where we shall continue with planetary chemistry. Thanks a lot.